Hello dear learners, welcome back to my YouTube channel. So today in this video we'll be discussing one derivation for class 12, both ISC and CBSE. So here we will be discussing the balance condition for a Wheatstone bridge, the working formula for the Wheatstone bridge. So as you know, a Wheatstone bridge is a device with the help of which we can measure the unknown resistance. So in this we have three known resistance, and using the formula we can calculate the fourth one. So as you can see in the circuit diagram, we have four resistances P, Q, R and S in four different arms of the Wheatstone bridge. So this resistance P is in the arm AB, Q is in the arm BC, and R and S is in the arm AD and CD respectively. And between these two junctions, that is the point B and D, we have a galvanometer. So a galvanometer is a device which can measure a small current, right? So from the point A and C, we have connected a battery and we have a key. So here we will be using the Kirchhoff's laws, and we will obtain the expression for the working formula of a Wheatstone bridge, which is one important derivation for class 12. So let's start the video. So as soon as we close the key here, we know that current I will flow in the circuit. So this current I, as it reaches the junction A, what will happen to the current? There will be two different paths in which the current can flow. So the current will split into two parts. So let's consider that the current in the arm AB is, let's say, I1, and current in the arm AD is, let's say, I2. So this current I, when it reaches the junction A, it divides into two parts, that is I1 and I2. I1 will flow through resistance P, I2 will flow through resistance R. Now again, when this current I1 reaches this junction B, again there will be two different paths in which this current can flow. So this current will further divide into two parts, that is a small current through the galvanometer, that is IG, because galvanometer can hold only a small current, so a small current IG will flow through the galvanometer, and the remaining current means from I1, IG is flowing through the galvanometer, so the remaining current will be I1 minus IG. So this remaining current will flow through the resistance Q. Similarly, at the point D, or the junction D, we have this current I2 reaching the junction D. Similarly, this IG is also reaching the junction D. So when these two currents meet at the point D, they will have only one path in which the current can flow. So what will happen to the currents? They will combine and flow through the resistance S. So the current through the resistance S will be I2 plus IG here. Now again at point C, or junction C, this current I1 minus IG will reach here. Similarly, this I2 plus IG will also reach here. So what will be the current that will come out of this point C? So let's see. So this current I1 minus IG combines with this current I2 plus IG. So if you open the bracket, I1 minus IG plus I2 plus IG. So what will happen? This IG and this IG gets cancelled because one is minus, the other one is plus. So we will have I1 plus I2. And this I1 plus I2 is nothing but this is the total current I in the circuit. Because as you can see, at point A, I has split into I1 and I2. That means I is nothing but I1 plus I2. So when the current reaches the point C, we are getting I1 plus I2. That will be directly equal to the total current I. So the total current flowing in the circuit will be I, but depending on different branch of the circuit, the value of current will be different. Alright, so this is the distribution of the current. So you have to understand this distribution. I hope you have understood the diagram. So here we will be using loop rule of Kirchhoff's. So which says that in any closed path of the circuit, the sum of the product of current and resistance will be equal to the sum of the EMFs in that closed path. So if you consider the loop means it has to be a closed path. So we will consider the loop. So A, B, D, A. So you have to make sure that the starting point and the end point has to be same. Only then it becomes a closed loop. You cannot write A, B, D. A, B, D will not be a closed loop. You have to have the same starting point and you have to end at the same point. So we have considered this loop A, B, D, A. So in this loop A, B, D, A, if you look at the arm AB, then we have the current as I1 and resistance is P. So the product of current and resistance will be I1P plus, in this arm BD, the resistance is G, the resistance of the galvanometer itself, and the current is IG. So the product will be IG times G plus, in the arm DA, current is I2, resistance is R. So the product will be I2R. And since there is no EMF connected here, so the value of EMF will be 0. So here we have used Kirchhoff's second law, which says that the sum of the product of current and resistance in the closed path has to be equal to the sum of the EMFs. So on the left hand side you can see we have the sum, that is addition of the product of current and resistance I1P, IgG, I2R. So these are the products of current and resistances and we have added them. So sum of product of current and resistance here, and on the right hand side we are writing 0 simply because we don't have any EMFs here. So this is using Kirchhoff's second law. Now what we have to do is we have to use the sign convention. Now which is very important while doing the Wheatstone bridge and numericals that we do from the Wheatstone bridge. Now the sign convention is very simple. For the current, if the direction of the path you have taken and the current are in the same direction, then the current is taken as the positive. The sign convention for current is taken as positive. But if the path taken and current are in the opposite direction, then the sign convention for current we will take it as negative. So let's use the sign convention here. So using the sign convention, you have to learn this sign convention for the current. As I said, it's very simple. Let's look at the first current I1, whether it will be positive or negative. So here we are going from A, B, D, A. That means we are moving in this clockwise direction. So for the arm AB, we are going from A to B. And you can see that this current I1 is also going from A to B. So the current and the path taken is same. So when the current and the path taken is same, the sign for the current we will take it as positive. So the sign for I1 will be positive. So we will write it as I1P itself. Now let's see what will be the sign for IG, that is the current to the galvanometer. Now from point B, we are going towards D. A, B, D, A. This is the loop that we have taken. So from A to B we have gone. I1 is positive. Now we are going from B to D. You can see that this current IG is also going from B to D. So the sign convention for IG will also be positive. So this will also be positive. So we have IG times G here. Now the third current I2. Let's see what will be the sign. Now we are going from D to A. We are going in this direction. From D to A. But look at the current I2. This current I2 is going from A to D. That means here the path that we are taking is from D to A and the current is moving from A to D. That means it is in the opposite direction. So if it is in the opposite direction, then the sign of the current will be taken as negative. So here I2 will be negative. So here you have to replace it with the negative sign. I2R equals to 0. So let this be equation number 1. So here we have used Kirchhoff's second rule, which is this one, sum of product of current and resistance in the closed path equals to sum of the EMF. And the second, we have to use the sign convention. If the current and path are in the same direction, current is taken as positive. But if the current and path are in the opposite direction, then current is taken as the negative. Now we will take another loop. So we will take this loop B, C, D, B. So we are taking the loop B, C, D, B. So in this loop B, C, D, B, again we will use Kirchhoff's second law, that is sum of the product of current and resistance equals to sum of the EMF. So in the arm BC, the current is I1 minus IG and resistance is our Q. In the arm CD, current is I2 plus IG, so I2 plus IG and resistance is S. And in the arm DB, current is IG and resistance is G and equals to 0. So here you can see on the left hand side we have the sum of the product of current and resistances in this given loop BCDB, and since there is no EMF we have written value as 0. So let's now use the sign convention. So using sign convention, so the rule for sign convention will remain same for current. So let's look at the first current, that is in the arm BC. So current is I1 minus IG. So we are going from B to C, and look at the current I1 minus IG. This current is also going from B to C. That means this current, the sign we can take it as positive. So I1 minus IG will remain positive. So no need to change anything here. Now let's look at the second current. We are going from C to D. So we are traveling from C to D, but look at the current I2 plus IG. It is going from D to C. That means the path taken and the current, they are in the opposite direction. So when they are in the opposite direction, the current will be negative. So this current I2 plus IG will be negative here. So we have written negative here using the sign convention. Now let's look at the current IG. So we are going from D to B. We are following this path B, C, D, B. We are going in clockwise direction like this in this loop. So we are going from D to B. The current is coming from B to D. That means it is coming in the opposite direction. So again IG will be negative. So let this be equation number 2. So we have used two loops ABDA and BCDB, and we have found out two equations, equation number 1 and equation number 2, using Kirchhoff's laws and sign convention. Now one thing you have to remember here is, for the Wheatstone bridge to work, it has to be under balanced condition. Now balanced condition means the current through the galvanometer here, that is IG, must be equal to 0. So we have done practical based on this, which is the meter bridge, application of Wheatstone bridge itself. So there you have seen that we have obtained the balanced point when the current to the galvanometer becomes 0 and the galvanometer pointer shows 0 deflection. So for the working of Wheatstone bridge, it has to be under balanced condition, which means the value of current to the galvanometer must be equal to 0. So we will take that into consideration. So you can write, at balanced condition, your current to the galvanometer will be 0. That means IG will be equal to 0. So let this be equation number 3. So we will put this value now in equation number 1 and in equation number 2. First let's put the value here. So putting equation 3 in equation 1. What do we get? In equation 2, in equation number 1, we have I1P minus plus IG into G, but the value of IG is 0, so 0 into capital G, minus we have I2R equals to 0. So we have taken IG equals to 0 here in equation number 1. So 0 into anything becomes 0, so we can write this as I1P minus I2R equals to 0, or if you take it to the right hand side, we will get I1P is equals to I2R. Let this be our equation number 4. So similarly, we will put the value of IG equals to 0 in equation number 2. So if you put IG equals to 0 in equation number 2, this becomes 0, this becomes 0, and this becomes 0. So let's put the value. So putting equation 2 in equation 3 in equation 2. So let's put it here. So I1 minus Ig is 0, so this becomes 0 into Q, minus I2 plus this again becomes 0, so 0 into S, minus 0 into G equals to 0. So we have just replaced Ig equals to 0 in equation number 2. So let's arrange this equation further. So here I1 minus 0 will give you I1 times Q will give you I1Q. Similarly, I2 plus 0 will give you I2 times S will give you I2S. And this term 0 into Z becomes 0, so no need to write, so equals to 0. So let's arrange this further. So we can write this as I1Q is equals to I2S. So let this be equation number 5. So using the balance condition, Ig equals to 0 in equation number 1 and 2, we get two other equations, that is equation number 4 and equation number 5. Equation number 4 we have I1P equals to I2R. Equation number 5 we have I1Q equals to I2S. So now what we will do after this is, let's divide equation 4 by equation number 5. So after this, dividing equation 4 by equation 5, what we will get? Left hand side will be divided by the left hand side. So we have I1P divided by I1Q, and right hand side will be divided by the right hand side. So I2R divided by I2S. So we are dividing equation 4 by equation number 5. So left hand side by left hand side, right hand side by right hand side. So here you can see we can cancel I1 and I1. On the right hand side we can cancel I2 and I2. So we will get this equation P by Q is equals to R by S. And this equation P by Q is equals to R by S is the working formula for the Wheatstone bridge. So this derivation is important, and you have to remember that Wheatstone bridge works when it is under balance condition, that is when current to the galvanometer is 0. So sometimes they will give the derivation, sometimes you will get the numericals. So you have to learn the sign convention and you have to know Kirchhoff's laws. Alright, so that's all for today. Hope this derivation is helpful for you. You can comment below and ask for any of the topic that you want to discuss. So see you in my next video. Thank you all.